Hello and welcome. In this video, we'll be covering section 5.2, which is over exponential functions and graphs. My goal for you by the end of the video is to be able to graph exponential equations and exponential functions, and to be able to solve applied problems involving exponential functions and their graphs. So we'll first start with what an exponential function is. Hopefully this is a review from something you've learned prior, but regardless, a function that's f of x equaling a to a power of x, where x is just any real number and a is a positive number that does not equal 0, is called a exponential function with the base a. What's important with this, again, is the base does have to be positive to avoid any sort of imaginary number, and the variable is always going to be up in the exponent area when it comes to these exponential functions. Alright, so let's go ahead and jump right on in. A little bit later in this video we'll talk about how we can maybe memorize some of the key points that these types of things go through. But to start, we're just going to, I guess, explore this by utilizing t-charts. So with this one, if I went ahead and just said, you know what, for this function where it's 2 raised to a power, let's maybe throw a couple of negative numbers into our t-chart, for sure throw 0 in, and then maybe a few positive numbers as well. So again, I'm just picking some random x's for my t-chart. I'll plug it in and see what I end up getting. So 2 to a power of negative 2, that would become 2 to the negative 2 power, which a negative exponent would drop to the denominator. And 2 squared really would equal 4, so I really could say that this first one is 1/4. The next one, 2 to the negative 1. Again, because of the negative exponent, it would drop to the denominator and become 2 to the positive 1, which would just really be a 1 over a 2. Third one here, anything to a power of 0 will always equal 1, so that one's relatively easy. 2 to a power of 1 would just stay the same, so that's going to stay at 2. 2 to a power of 2 is 2 squared, so that would be 4. And 2 to a power of 3, that would be 2 cubed, so 8. So at this point, we'll go ahead and throw some of these points on our grid. So at negative 2, I was at 1/4. At negative 1, I was 1/2, so just a little bit bigger. At 0, I'm at 1. At 1, I'm at 2. At 2, it's at 4. And at 3, it's all the way up here at 8. And if you think in terms of could this ever actually equal 0, well, there's really no way I could actually become 0 if I'm raising 2 to a power. So this actually does have what we would call a horizontal asymptote really close to the x-axis, that then as I go through these points, notice once I pass that y-axis, it ends up growing significantly faster, whereas on the left side it just keeps getting closer and closer and closer to 0, but never actually would equal 0. We'll go ahead and try another one. For this one, we'll make a similar t-chart, and we'll just kind of see what happens and make a decision. So I've got my x's. Let's go negative 2, negative 1, 0, positive 1, positive 2, and just see what happens. If I need to go positive 3, cool. If I need to go negative 3, just for some extra points, let's go for it. But anyway, we've got our x's. Now we'll just figure out our y's by plugging in. So this first one would become 1/2 to a negative 2 power. Well, what a negative power would do to a fraction is actually flip it, so this would become a 2 over 1 to now a positive 2 power. Well, 2 over 1 is just 2, and 2 squared would equal 4. Similar thing's going to happen here with negative 1. So 1/2 to a negative 1 power actually would turn into 2 over 1 to a positive 1 power, which really just equals 2. As before, anything to a power of 0 would equal 1, and then anything to a power of 1 stays the same, so 1/2 to a power of 1 would stay 1/2, and 1/2 squared would be really a 1/2 times a 1/2, which would be a 1/4. So notice what's happened with this is when my base was something that was less than 1, in this scenario it was the 1/2, it actually is going to kind of look like it flips over the x-axis, and I'll kind of show, or sorry, flips over the y-axis when it's all said and done. But let's go ahead and plot these so we can actually physically see it. So negative 2 was up here at 4. Negative 1 was at 2. 0 was at 1. 1 was at 1/2. And 2 was at 1/4. So notice it's kind of doing the exact opposite. So if I really wanted to, I could go ahead and plug in -3, which would be like 1/2 to a -3, which is 2 over 1 to now a +3, which would equal +8. So if we wanted to graph one extra point, since it's technically going to fit on this grid, notice what happens now is as I go further to the right it becomes closer to 0, but as I go further left it actually is relatively steep. So this one now, notice, decreases the entire time. So kind of the moral of the story here is, if your base is ever less than 1 but greater than 0, then at that point it's going to be a decreasing graph. Whereas when the base was greater than 1, like the previous example, such as 2 to a power of x, that one, notice, it increased. Some things that they still had in common is they still went through the 0, 1, and they also both had a horizontal asymptote, or they would approach the x-axis as it reached its extreme. So in this case, as I went to the far right, it would approach the x-axis, whereas when the graph was increasing, it was the far left would be approaching 0. Now, using those two examples that I just worked through as kind of our basis here, there actually happen to be some properties that hopefully we paid attention to that happened. So again, with each of these, they have the format of a being raised to a power of x, where a does have to be positive, and it just cannot equal 1. Both scenarios, if you looked at what we had, would be things that were considered continuous. They also would pass the horizontal line test, so we would be able to consider them 1-to-1. They did go forever left and forever right, so the domain would be all real numbers. However, it never dropped below the x-axis, so my range would actually just be from 0 to infinity, where I make sure I actually don't include 0 because it never actually would touch the x-axis. When the base was greater than 1, it would be an increasing graph, whereas anytime it's a proper fraction or a number that's between 0 and 1, it would be decreasing on the entire graph. Both scenarios always have a horizontal asymptote that would be the x-axis. It's just a matter of, is it going to approach it on the left side or is it going to approach it on the right side? And again, that's dependent upon what type of base you have, whether it's greater than 1 or between 0 and 1. Both did have a y-intercept at 0, 1, and some other key points if you kind of think in terms of what would be some nice easy numbers to plug in instead of having to t-chart every single time, is if the power was 1, it would remain the base, so 1, a. -1 is going to flip the base, so it would turn into the reciprocal, or -1, 1 over a. And then another one that oftentimes will still fit on our grid, may not always, depending on how big the base is, but 2 is always going to be paired with whatever the base is squared. So if we kind of keep an eye out for those 3 key points plus the y-intercept and your horizontal asymptote, we should be able to graph this very similarly to how we graphed earlier in the year, which was utilizing transformations. So speaking of which, let's go ahead and review kind of how those transformations happen and what potential places numbers could be. So if we look in this example, I've kind of switched the base now to be a b. No big deal, it was more just trying to work alphabetical through this. But if I have some coefficient in front, in other words, if I multiply by a, because of the position, that would be outside of the function. Remember, when you multiply it outside, that would be a vertical stretch or shrink, depending on if it was greater than 1 or between 0 and 1. If b was considered the base, notice we could have multiplication inside. Well, if you recall, multiplication inside was actually a horizontal stretch or shrink, depending on the value of c. What's kind of key with that is we do always have to make sure that it is fully factored out of whatever, if there was addition or subtraction, I would have to factor it out. So it could have potentially had, I guess, distributed through cx minus ch. But again, notice we would want to factor that number out to be able to identify the next part, which is addition or subtraction on the inside is always going to be a horizontal shift, whereas addition or subtraction on the outside for the k would be a vertical shift. Now, if we end up having something where the a value was negative, remember a negative outside would reflect something over the x-axis. If the c had a negative on it, then it would actually be reflected over the y-axis. So kind of keeping an eye out for all of those things that we learned in the past, they're still going to hold true for this particular function. It's just a matter of the key points that we'll be passing through, and what the shape of the graph will be is going to be a little bit different than some of the other functions that you've dealt with. So let's go ahead and try one out. With this one, instead of having to do a t-chart, we can just think in terms of where do these points go. If you want to make a t-chart, there's nothing wrong with that, but ultimately if I said describe the transformation, if I see here I don't have any numbers multiplying in either spot, so I don't have any stretching or shrinking. All I have is subtraction inside, so subtracting inside, recall, should move our graph to the right. So subtraction inside would then mean it's a shift to the right, and then however much is being subtracted, which in this case is 2. So I could now just take each of the key points. Shifting horizontally is not going to change my horizontal asymptote, so I know I'll still approach the x-axis and not cross it. But my y-intercept that should have been at 0, 1 now should be 2 places to the right, so it would be at 2, 1. The 1, b would be, in this case, 1, 2. That should be 2 places to the right, so that would be at 3, 2. And this negative 1, 1 over b, so in this case negative 1, 1/2, that one also should be moved to the right 2 places, so now it would be a positive 1. So that gives me what looks like enough. I feel like probably 2 squared, or the 2 with the base squared, would also fit. So 2, 4 should have been on the original graph, but again it's been shifted to the right 2 places, so now it would be at 4, 2, or sorry, 4, 4. So again it gets really close to the x-axis, and then start swooping up through these points, and the reason that this one is increasing once again is because that base was greater than 1. We'll try another example. This one, notice I still have the same base function, still base of 2, but this time there's subtraction, however it's outside. So notice this one has subtraction outside, and anything that's being subtracted outside should be a vertical shift, and specifically in this case, since it's a minus, it would be down and then whatever the amount is, which in this case is 4 places. So that would change our horizontal asymptote from being the x-axis to now being out at -4. So I'm going to go ahead and just draw that as a reference line that I know I shouldn't cross over that. And then each of the key points, so 0, 1, moving down 4 places would turn into 0, -3. 1, 2, if I move that down 4 places, would turn into 1, -2. 2, 4, move down 4 places, will turn into 2, 0, and I guess we could technically do -1, 1/2. Move that down 4 places, it would turn into -1, -3.5. And so now notice I can start close to my reference line that I had, and go ahead and make sure that I spike up on the right, because again the base was greater than 1, so it should have been an increasing graph, which as we can see that did happen. Let's go ahead and do one more example, this time with a base that's less than 1, or between 0 and 1. If I were to reorder this technically would be like a -0.5x and then plus a 5. So if I were to try and describe each of the things, the negative in front is going to reflect over the x-axis. My base in this case is just the 0.5, so I'm just going to identify my base in this case is 0.5, or you could also say that that would be 1/2. And then the plus 5, that should move our graph up, because it's outside the function. It should be a vertical shift, in this case up 5 places. So the up 5 is going to change my horizontal asymptote, so I'm going to go ahead and just add 5 to 0 and get 5. And instead of this being above the line, because of the reflection over the x-axis, it would be below. So in order, I would have to do the reflection first, because that would be like multiplying by -1 before I do the up 5, because that would be addition. And multiplication should always happen before I add or subtract. So as far as the key points that I'd have, 0, 1, if I reflect it, would turn into 0, -1, and then moving that up 5 places, that would turn into 0, 4. And do the same thing here with the -1 comma the reciprocal. So if we think back to the original graph, -1 actually turned into 2 for this function. So -1 comma 2 reflected would turn into -1 comma -2, and then shifted up 5 places would turn into a -1 comma 3. -2 I could also do. -2 should actually, on a power or a base of 1/2, turn it into 2 to the positive 2 power if I use the negative to flip the fraction. So it would have been -2 comma 4 reflected over the x-axis would turn into -2 comma -4, and then shifted up 5 places would turn into a -2 comma 1. At +1 it would have been at 1/2. Reflect that across, it would be -1/2, and then add 5 to it. That would turn into a +4.5. So notice the shape of this graph now actually was going to be increasing, but only because it was a decreasing function that got reflected over the x-axis. So notice this was now more of an upside down version of the graph. So this would have actually completely flipped my range. Instead of being 0 to infinity, it would have been -infinity to 0 before the shifting up by 5 places. So the up by 5 places actually changed my range to be -infinity until I get to +5 instead of the 0. So now that hopefully we have the basics of just how these graphs would be, I guess, created and how they can be shifted, let's go ahead and deal with applications as well as some special exponential functions. So the first application is going to be being able to compute interest on an investment. So notice the formatting of this is the A equaling our principal, or the amount that you start with, times, and then inside your parentheses you'd have 1 plus the rate in decimal form over the n, which is the number of times compounded per year. So usually the n is something that's dependent upon a word that you read in the expression. Things such as semi-annually or annually or let's see, quarterly or monthly. Each of those kind of have an implied amount of times per year where that would happen. Annually would be like 1, semi-annually would be 2, quarterly would be 4, and so on and so forth. And then it would have to all of that to a power of n times t, where the t is presented in terms of years. So this first example that I'll work through utilizing that formula is essentially just coming up with first, what is the actual function for this investment based upon having $100,000 invested at 6.5% interest and compounded semi-annually. And then the second part will actually be computing out some specific amounts at specific times. So let's go ahead and try building our expression here, or our function. So for this one, it looks like I've got the end amount in terms of t, so the a function of t is equal to our principal, which should be how much I started with, so 100,000. So again, that would be the p. This 6.5% interest, that would really be the r, but it was, as you can see, presented in percent format. So I'd want to move the decimal twice to the left, which would then give me 0.065. The other way you can do that is divide it by 100, hence the name percent, where cent implies 100. And then compounded semi-annually, that lets me know that n in this case is equal to 2, because semi-annually would be 2 times per year. So filling in the blank here, I've got my p identified times 1 plus the rate in decimal form, so 0.065 over the n, which was 2, and then to a power of 2 times the time, which I don't know because that again is my input variable for this specific function. So notice again, the kind of trickiest part of all of that is just remembering to rewrite your rate as a decimal. If you didn't rewrite it as a decimal, you end up getting some numbers that really would not make sense in at least the real world sense. So if you ever do get some numbers that seem way larger than maybe they should be, more than likely what we've forgotten is to go ahead and convert a percent into a decimal form. Now The second part of this problem was to actually compute out some specific amounts at specific times. So let's go ahead and just compute each of these for different values. So a of 0, if I plug 0 in where I see that t, so this is really the only place I'm plugging in, that would give me a power of 0 on that parenthesis. Well, anything to a power of 0 would just equal 1, so I'd end up with 100,000 times 1, so that would just equal 100,000. Which, if you think about in context, if the time was 0, that means that there hasn't been any time to actually compound anything, so that should, at time equaling 0, always just equal whatever your initial amount was. If I move on to the second one, a of 4, typing into the calculator ultimately is what's going to happen here. This would turn into 129,157, and it looks like 75 cents-ish. If I move on to the next one, plugging in 8, I'd end up with now having a power of 16 up in that area. So if I were to take the time to compute all of that, that's going to turn into let's see, 166,817, and it looks like about 25 cents this time. And then the last one here at 10, turns into what looks like 189,583 and 79 cents this time. So probably the trickiest part of the actual computing these is just making sure that we have it typed in correctly. I personally like going ahead and just multiplying whatever they're plugging in, so I don't have to actually type in 2 times 10 or whatever. In this case, 2 times 10 turning into 20 wasn't too tough, or 2 times 8 turning into 16, and so on and so forth. And then as far as the inside is concerned, I basically just try and type it in exactly as it looks, just inside a parenthesis grouping. That way I don't have to worry about, I guess, retyping it, and then I just copy and paste from the previous line, so I don't have to completely start over each time, especially if you have to do multiple numbers like this one wanted us to do. Now the second thing I wanted to bring up in this kind of applications or just extension of exponential functions here is there is a number e that exists. So similar to like pi representing a specific number, hopefully we know to be like 3.1415 and so on and so forth, that was irrational. There is also a number e that exists that's very similar. So again, just like pi was a symbol representing a number, e is a symbol that represents a different number. In this case, it came from Leonard Euler, who ended up naming it, hence the e being the value. It does not ever terminate or repeat, meaning it is irrational, and it happens to be constant, so it's not like you ever have to solve for e. So if you ever see this lowercase e in an expression, it's not a variable, it just is representing this idea of about 2.72-ish, or as you can see, it's a decimal that just keeps going on and on and on and on. Now, as far as the first thing to do is just practice number one, make sure that we know where that button is on our calculators. Every scientific calculator or graphing calculator should have an ability to evaluate out something that looks like an e to the x. Sometimes it's the main button itself, sometimes it's the second function of a button. So with whatever calculator you're using, make sure that you're comfortable identifying where that button is. But if I were to just evaluate each of these things out utilizing a calculator, on mine it's the second function of the natural log button, so it actually is the button that has like ln written on it. So if you see the ln button on your calculator, more than likely the e is somewhere close to it. If I were to just figure out this first one, e to the third, it comes back approximately 20.0855, just to follow the instructions of 4 decimal places out. If I did the next one, e to the negative 0.23, notice it can be an ugly exponent, it still is okay. This one comes out 0.7945. And then the last one, shouldn't really even need to type this one into the calculator. Anything to a power of 0 would just equal 1. So we'll go ahead and box up our answers for this one. But notice there's really no work to show. It's just pressing buttons on a calculator, just getting familiar with making sure that you know how to actually type these in. So on your own, I'd recommend whatever calculator you're using, just make sure that you can verify each of these three numbers. If you can, then that means you're more than likely plugging things in correctly. So why even talk about E? Well, with exponential functions, there actually are quite a few applications where the exponential function will end up having this base of E when it's all said and done. So everything from here, I'm just going to talk about how does that graph really work, or how would I actually need to make that graph. And ultimately, it's not going to be perfect because, well, E is just a irrational number, but I can at least get relatively close to where it should be. So for this first example, I'm just going to graph the or f of x equals e to the x. If we follow the pattern from earlier, the common points, notice there's no addition or subtraction or multiplication, so this is just the very basic parent function with e as the base. So I know it should go through 0, 1, as well as -1, the reciprocal of the base. So if I were to try and figure out what is 1 divided by e, in this case it would turn into approximately, so 1 over e, wrong color, would be approximately equal to 0.37-ish. So since that's not going to be a precise value, I'm just going to pretend like it's just a little bit less than a half at -1, and then 1 is at whatever the base is. Well, the base of e is approximately 2.72-ish, so I'm just going to go a little bit more than 2.5. And if I were to square e, it would become a little bit larger than this grid allows. So this one, as far as the graph is concerned, would be something that looks just like this. Again, is that perfect? No, because, well, it's almost impossible to be 100% accurate when it comes to plotting decimals, but we should be able to at least get it in the right ballpark. And notice that you can definitely tell that that was a base that was greater than 2, but definitely less than 3, just based on this point right here. So just try and do your best when it comes to graphing these types of things and make sure that that's actually happening. Next type of problem to deal with, or the next example I'll work through, is what is going to happen if it was e to a negative x power. Well, first off, a negative inside of a function reflects it over the y-axis. So the point that actually lies on the y-axis at 0, 1 would remain the same, but the point that was over here at 1, 2.7-ish now is going to be at -1, 2.7, so right about there. And then the other one that was at -1, 0.4-ish now is going to be at +1, 0.4-ish. And so notice this one now becomes a decay model, or it's going to decrease as I go through the points. So another way we could have written this is e to the negative x is also the same as a 1 over e to the positive x. So just like we had earlier when we had a base that was less than 1, notice this would turn into now something that's decreasing the entire time. So you can interpret bases that are less than 1 as negative exponents, if that helps, where you then could flip the base and make it greater than 1. If that makes filling out a t-chart easier, that way you don't have to worry about negative exponents. But regardless, notice either of those representations kind of confirm that yes, it should be decreasing as we go. So let's go ahead and practice a few more, just with different types of stretches or reflections or shifts. This first grid, I'm just going to go through and do this part A. So notice with this one, e to the x plus 3, ultimately that plus 3 right there would be a shift to the left 3 places. So I'd take all of my original points, which if I were to plot them again on here, it would have been 0, 1, 1, 2.7, and -1, 0.4-ish. If I just took each of those points and moved them all left 3 places, my smallest one would be right there now. The 0, 1 would be at 3, 1, and the 1, 2.75 would now be at -2, 2.75. So notice each of those points I just shifted to the left 3 places. And now notice I could draw my final graph that would go something like that. So the next example, I've got a little bit more going on. I do have a vertical stretch. I do have a subtraction inside, so that should be a shift right 1 place. And then I do have subtracting 2 outside, so that should be a shift, and specifically down 2. So again, we can think in terms of our original points, 0, 1, -1, 0.4, and 1, 2.7-ish. And just move each of them accordingly. So my horizontal asymptote of 0 now is going to be down here at -2. So I'm going to go ahead and just use that as a reference. And if I were to stretch each of these by 2, if I double 0.4, that would be about 0.8. Then shift it to the right 1 place and then down 2 places, I'd end up right about here, which would be like maybe -1.2-ish. If I do the same thing with 0, 1, first I would double it by the stretch, so that would turn into 0, 2, move it to the right 1 place, and then down 2 places. I'd end up here at 0, 1, or sorry, 1, 0. The next one, if I were to double the 2.7, if I double 2.7, let's see, what would that be about? Be about 5.4, so it'd be just a little bit above the grid. Then move it to the right 1 place, and then down 2 places. Looks like it would turn into right about 3.4-ish. And so notice now my grid has, or my graph, sorry, has now kind of steadily increased as I went from right, or from left to right. In other words, it was now, because of the vertical stretch, going to increase faster than the original graph had. So notice that point at 2 was definitely further away from our horizontal asymptote than the other one had been, and in fact it was twice as far away. Alright, so now on to the last example. So for this one, what's a little bit tricky is now the 1 is in front as opposed to at the end, so what you can do right off the bat is just go ahead and rewrite it so that that number is in a more appropriate or more expected location. So I could rewrite this as -e to the x plus 1. That then tells me that this negative is forcing a reflection over the x-axis. And then the plus 1 that's outside, since it's adding outside of the function, this right here should be a shift up 1 place. So once again, if I were to take my original 3 key points, I've got 0, 1, I've got 1, 2.7, and I've got -1, 0.4-ish. So if I were to take each of those points and first reflect it, I'm going to go ahead and switch color just to make it stand out a little bit more. So -1 would now go to -0.4, and then shift it up 1 place. That would turn into just a little bit above where it was before. My horizontal asymptote of the x-axis, because that's being shifted up 1, I'm going to go ahead and actually just put that on my grid. I know I'm not going to cross that, but notice it is below it because, again, I'm reflecting over the x-axis, or it's supposed to be an upside down graph. If I do a similar thing here with the 0, 1, first reflected over the x-axis, so it would go to 0, -1, but then shift it up 1 place, it would actually go through now the origin. And then 1, 2.7, if I were to reflect it, would turn into 1, -2.7, and then shift it up 1 place would turn into a -1.7, or 1, -1.7. So this final graph here is going to flatten to the left, and then come down the page from left to right to create that graph. So notice again, I just took the original 3 key points and just took it on the journey they were supposed to do, the reflection first, followed by the shift to second, because again, multiplying by a -1 has precedence in order of operations before adding 1. And I just plotted what their new location was, and in the end, just connected them in a nice, smooth, continuous fashion. So anyway, hopefully this video has been helpful with getting the idea of how to graph these exponential functions. But as always, if you have questions, just reach out and let us know, and we'll do what we can to make it make sense. As always, I appreciate you taking the time watching your video, and we'll catch you next time.